we will see how we can build a passive analog first order low pass filter on a breadboard and test it using commonly available laboratory equipment such as a function generator and an oscilloscope. To start off with, the passive first order filter contains only two components. One is a capacitor and the other one is a resistor. This is also known as an RC filter. Here we have to use an unpolarized capacitor, and I will be using a mylar type capacitor, but even a ceramic disc capacitor is suitable for this situation. According to the schematic given, I will try to connect the capacitor and the resistor to my testing equipment which I have here, a function generator and an oscilloscope. The trick here is to use as less of wires as possible and the minimum space available in the breadboard, because common problems that can occur in this experiment are due to problems with the breadboard or due to the problems in breadboard wires. So if we try to minimize the space occupied in the breadboard, as well as if we try to minimize the number of breadboard wires that we will use, the practical will be a success. So first of all, I need to connect the positive terminal of my signal to one end of a resistor. So I will just connect the positive terminal to this resistor. Okay, like this. Then I need to connect the capacitor, one end of the capacitor to that resistor. And the other end of the capacitor should be connected to the negative pole. So I will just connect it like this, and as you can see in this construction I have used the minimum space and I have not even used a single breadboard wire for this connection. The only two breadboard wires I need to connect are for positive side, signal positive, I have to connect one breadboard wire for this resistor, and also for the ground pin I need to connect one breadboard wire, and also to get the output of the filter, which will be here, I need to connect another breadboard wire. So altogether I only have to use 3 breadboard wires. So I will use a green wire to connect the ground. So this is the ground breadboard wire, and another breadboard wire for the positive, and then I will connect the breadboard wire here, as this is the output. So this is the simple construction of a first order passive analog low pass filter consisting of a single resistor and a single capacitor. Now that I have constructed the circuit in the breadboard, I need to make the necessary connections from the function generator side and to the oscilloscope side. And in the oscilloscope I will be using both the channels. First channel I will use to monitor the input signal that is coming from the function generator, and the second channel I will use to measure the output signal. So here I can just connect. So this is the positive end, so I will just connect the positive terminal, and also make sure that these connections are as tight as possible, otherwise the circuit is very sensitive and there may be errors occurring later on in the experimentation process. And I will connect the ground wire just like this, and after that I have left with the output wire. So first of all I will take one oscilloscope probe. This is the oscilloscope probe that I will connect to the input side. So this is my input wire. So I will just connect the probe to this end, and I will then connect the ground wire. And then I need to connect the output, so I will take the second channel probe and connect the output. So here I will connect it to this probe. So this is the output wire, and then I will connect the ground. So as you can see, it is a little messy if I take a close up, However, this setup is intentional as this limits the amount of wires that I have used, and it reduces the complexity of the experiment and the number of points where the circuit can go wrong. So this is my signal. I have the red wire coming from the function generator, and this is the corresponding breadboard wire that is going to the breadboard, and then I have the channel 1 probe of the oscilloscope connected, and then here I have the output signal wire connected to the second channel probe, and everything is grounded. Here I have connected all the crocodile clips together. It may seem messy at this stage, but it is intentional to avoid any complications in the experiment. Now that we have successfully constructed the circuits and connected it to the necessary testing equipment, we need to set up our oscilloscope. As I have mentioned in the oscilloscope and function generator familiarization video, first of all you need to press the default button to ensure that every setting is resetted, and then I will enable channel 2 as well, because here I will be using both the channels. And when it comes to the measurements, I need to measure both the amplitude and frequency of the input signal and output signal. So for that I will click the measure function and I will select add measurement. So I will be adding it first to channel 1. I will be going to the amplitude measurements, peak to peak is what I need, and then I will go to the frequency and I will select the frequency. So I have the frequency and amplitude of channel 1. To get the measurements for channel 2, I need to click the source and I need to go to channel 2 and select it. Again I will insert the frequencies like this. So this is the peak to peak measurement, amplitude, and then I will insert the frequency. And if I get rid of all the menus here, now in the measure tab I have the peak to peak amplitude of channel 1, I have the frequency of channel 1, I have the peak to peak amplitude of channel 2 and frequency of channel 2. Now my oscilloscope is all set up for our experiment. Next up, I need to set up my function generator. According to this experiment, I will be using an amplitude, a peak to peak amplitude of 5 volts, and also the frequency is what I will be changing, that is my independent variable, and I will be using a sinusoidal function. So first of all I will go to the sinusoidal function and I will select the amplitude and select it as 5 volts peak to peak. Now my amplitude is set up. The frequency however is different, because frequency you have to change. According to this experiment I will go from 10 Hz and I will keep increasing it until I reach 10 kilohertz at decade in 10 intervals. That means I have to go to 10 Hz, 20 Hz, 30 Hz, 40 Hz until 100 Hz. Then I will move on to 100, 200, 300, 400, 1000 and 10,000 respectively. That is the experiment procedure. So first of all I will set up my frequency to 10 Hz to start off the experiment. Now I will click the output button in the function generator and it should display a waveform in the oscilloscope. So I will press the auto set button to make sure the graphs are scaled, and I will use a manual adjustment to get it to same position. So my two signals, although they seem one signal, it's actually like this. So on the yellow color line I have my input, and on the blue color line I have my output. So this is the signal, and now if you see, I will get a close up. Initially at 10 Hz my input amplitude is 5.36 volts and my output amplitude is 5.28 volts. So in filters you need to obviously know your cutoff frequency. So here we are using a 100 nanofarad capacitor and a 1.5 kilo ohm resistor. If you use the equation, that is cutoff frequency equals 1 over 2 pi RC, and if you plug in these values you will get a cutoff frequency of approximately 1 kilohertz or 1000 hertz. So that is my cutoff frequency. So right now I am at 10 Hz However, if I keep increasing the frequency, and when the frequency reaches near 1000 Hz, this output amplitude will start to decrease. That is my experiment. So what I have to do is take down these measurements at each frequency. So first I will start off with 10 Hz and I will take down my input voltage, output voltage. So the frequency, input voltage and output voltage, that is what I will be writing down as my results or observations. Start off with 10, then increase to 20, then increase to 30, take the readings at each value, then go to 40, take the readings, 50, like that, go until 100 Hz. And then you have to take all those readings. Now you can actually use the manual adjust in the horizontal scale to actually scale the graphs properly, and then you will see the values. Here I have an input of 5.44 volts approximately and an output of 5.36 volts. So still the output amplitude has not decreased in a low pass filter. All the low frequencies will be passed through and high frequencies will be, high components will be attenuated. So still it is not attenuated because we are just at 100 Hz, not 1000 Hz, close to our cutoff frequency. So we will keep increasing. So I will go to 100 Hz. So now I will actually zoom in on the readings itself, because then the change can be identified clearly. So 200 Hz, 300, 400. Now you can see I am at approximately 500 Hz and the output amplitude has decreased to 4.72. So like that I can keep increasing, and I have reached 1000 Hz, and at 1000 Hz the amplitude, which was originally 5 volts, has decreased to 3.84 volts. According to an ideal low pass filter, this should be 0, but we are not considering the ideal circumstances because we are dealing with practical circuits and practical components. Therefore, the attenuation won't be instantaneous, it will be a smooth gradient. So what you can do is keep increasing the frequency and take readings until you hit 10 kilohertz. So that is what I am going to do. So now I am at 1 kilohertz, so I will go to 2, 3, like that. I will increase up to 10 kilohertz. So now my frequency is at 10 kilohertz, and this is a really good observation. The yellow color line is my input waveform, which is very large in amplitude, and the blue color wave is my output waveform, which is very small. So I will again just use the scaling of the horizontal axis. Now you can see at 10 kilohertz my input is still at approximately 5 volts, but the output have actually died down to 560 millivolts. This is essentially the operation of a low pass filter, a passive analog first order low pass filter. You can repeat the same experiment and the same procedure for a high pass filter as well. Only difference is the circuit configuration. The position of the capacitor will be swapped with the position of the resistor. And also you can use the similar technique, the similar experimentation procedure for a band pass filter as well. Band pass filter is essentially the combination of a low pass filter and a high pass filter. Band pass filter does not allow the initial frequencies to pass through, then it will allow some frequencies to pass through, and again it will stop all the frequencies from passing through. Essentially, in a band pass filter you have two cutoff frequencies, one at the lower end, one at the higher end. So whatever your passive analog filter is, you can follow this exact procedure to do the experiment and test your filter. Now where are these readings are being used? You can plot a body diagram. After you have plotted a body diagram, you can do all sorts of analysis like obtaining the actual 3 dB cutoff frequency and etc. However, the procedure for low pass, high pass, band pass remains the same.